Okay, off we go. So last time we had just gotten through stating Gauss's divergence theorem. And a reminder, this theorem fits into a kind of a template of theorems that we talked about, which are basically, short version is, if you can identify an accumulating quantity, any sort of accumulating quantity, stuff being a nice example of accumulating quantities, right? Well, it turns out all accumulating quantities, you can pretend like they're stuff. There's a corresponding stuff density, and you can compute the quantity as an integral of that density, right? Just like with any kind of stuff. And the trick is just identifying clever accumulating quantities, right? So what we noticed last time was that boundary flux, and again, casually speaking, we just say flux. It's just understood in a context like this that we mean boundary flux. Flux is an accumulating quantity. So that quantity, because it accumulates and because stuff is density times size, the density being divergence, as we discussed last time, boom, there's your theorem. Just like Green's theorem, just like fundamental theorem of calculus, just like the two-dimensional divergence theorem, right? We have accumulating quantities of which we integrate their densities to get the total. And it's just the same idea, different context. So Gauss's divergence theorem, like so. Now I will warn you, there is a catch on this, as with all of these theorems. This one in particular, the catch is that these fluxes literally, it says so right there, it's got to be a boundary flux, right? That's part of what makes this accumulate as we've described. So non-negotiable, it's got to be a boundary. And it's a very, very common mistake. I see this all the time, and it makes me cry a little bit every single time I see this. If a student forgets that, they will get garbage, nonsensical answers that have nothing to do with reality. So please be very, very, very careful. Only apply this if you're looking at a flux through a boundary. All right, so with that in mind, let's do an example. Here we go. We are looking at, let's see here, the unit sphere. Oh, wait a minute. Inward-oriented unit sphere. So this surface that we are given is like that. Is that a boundary? No. Right, keeping in mind the word boundary is a loaded word. Right? You got to be super careful. The word boundary means along with the understanding of a convention about orientations. So that's part of the deal. Is this a boundary? No, in that strict sense. Okay. Frustrating, but here's the thing. The inward-oriented unit sphere and the outward-oriented unit sphere that is a boundary, they only differ by their orientation. And an orientation is just a minus sign in the resulting integral. Right, so we're going to pull the same little fast one that we did in our first example using Green's theorem, which is to say that the surface in question, it's not exactly the same as the boundary, but it differs just in orientation and therefore just in that minus sign. Everybody good so far? I haven't used the divergence theorem yet, right? But I just have to kind of tweak the problem in such a way that the divergence theorem actually applies. Okay. All right. Cool. That noted, the computation we're doing now, you can see it right here, it just says this is an integral over S minus. S minus is a boundary, literally, strictly speaking, orientations and all. So, okay, awesome. I can compute that. Because it's a boundary, I can compute that with the divergence theorem. Let's come up here. The divergence theorem says boundary flux is a triple integral of divergence. So here we go. Boundary flux is triple integral of divergence. And of course, that minus sign comes along for the ride, as of course it must. Is everybody good? Everybody's happy? All righty. Okay, well, so yeah, a couple little details to worry about here. We've got to compute divergence. I claim divergence ends up being this, 3 plus x. Don't forget how to compute divergence. This is just a computational little deal, but it's the x partial of the first coordinate, which is just 3, and then plus the y partial of the second coordinate, which is x, and then plus, let's see, the z partial of the third coordinate, which of course is 0. There's no z's in there even. And so the divergence is just 3 plus x. That's a convenient little calculation. And it's basically all over but the shouting. We have an integral to be computed, and compute by whatever might be your favorite method. A lot of people would look at this and say, well, it's over a ball. Balls are easily understood in spherical coordinates, and you can write this in spherical coordinates. It will totally work. It's not even all that bad. Feel free to do it that way. I like to point out, though, and the following happens fairly often, I'm going to say, in my experience from way back when. And that is, sometimes when you have an integrand that is a sum, amazing things happen when you just break that up as two separate integrals. And look what happened here. Our original integrand is not a constant. It is not odd. But when I break it up, the first integrand is a constant, which makes this an easy integral. The second integrand is odd, which makes this an easy integral in a different way. Symmetry argument. Make sure to supply those details, think it through, right? Therein lies the devil, right? Don't just assume, right? I mean, you got to be really careful about symmetry arguments. But anyway, details to be supplied by y'all, but these integrals both work out very easily, and nice, easy final answer. How we doing? For your consideration, y'all may recall, one of the reasons I love symmetry arguments and geometry arguments is because of how often it came up when I was, cranking out integrals, however many decades ago that was. And I quoted some, I think, pretty impressive statistics, like 20% of the integrals I saw were zero by symmetry, right? Many, if not most, of that 20% were like this. It wasn't the original integral that I was asked to compute, or it wasn't the original integral that came up in, from whatever the physics was. It was after having broken it up into pieces, like I did here, that opportunities like this arose. Right. So this is a really slick idea and very important to allow you opportunities to capitalize on powerful tools. Everybody happy with this example? Okay, couple, let's see, 3 or 4, I guess, physics examples. I call these examples. They're kind of applications. And they're also what I like to call metaphors. So there is a case to be made that, now everybody knows that math can be used to solve physics problems. It's a valuable tool in solving physics problems, right? I think some of these examples, this being a pretty nice one we're about to go through, the physics actually provides a way of thinking about the math ideas. The physics can actually help you understand the math. And that's my primary interest in the several examples that I'm about to show you. Well, I mean both. I mean, obviously I want to show you some cool physics that you can do with the math also. But anyway, do keep in mind it goes both ways. Okay, so starting with the idea of a light bulb. Light bulb, of course, has a light source at the center, little LED these days. Right, little teeny tiny little itty bitty little thing, but it's inside a much larger glass bulb that I'm going to represent here as a sphere for convenience. Okay. All right. Now, what do LEDs do? Well, they generate photons, right? They produce little particles of light called photons that shoot out every which way, all different directions. Okay. And it turns out that the light bulb, the flow of photons flowing like a fluid, as I've kind of got drawn here, is inverse square radial. And just a quick comment, a lot of people get weirded out by this because, wait a minute, I thought the speed of light was constant, right? This doesn't have a constant magnitude. What are these photons slowing down? Nope. So what this is, you got to keep in mind, depending on the situation, sometimes your vector field doesn't represent velocity alone. Sometimes it represents velocity times density. And this is one of those times. So if you think about it, as photons go farther from the bulb, they also get farther from each other. And in fact, the photon density is less farther away from the bulb and greater closer to the bulb. There's just more photons closer to the LED. Does that make sense to everybody? So there's therefore more flow per unit area. Okay. All right, so inverse square radial, that's going to be relevant to us in a few minutes. Let's think through for a second. We've got a vector field. The vector field represents flow of fluid. When you have a vector field, you can talk about the divergence. How would we compute the divergence? So I'm going to compute the divergence in a couple of places. We'll start by looking at some point like along in here, let's say. Let's compute the divergence at a point like that. And I'm going to compute this with kind of a physics argument, but I think this is a really helpful physics argument, which is if I were to put a little sphere around that point, and let's talk about how light flows in and out of that sphere. Well, modest proposal. Every photon that goes in subsequently goes out. Right? So the net is zero. Right? There's a certain amount of, positive, what would we call it? Negative flux. Keep in mind, positive means outward. So as the photons go in, that's negative flux. But then as the photons go out, that's positive flux. And they have to balance because, again, everyone that goes in also goes out. So altogether, the flux is zero on this little green sphere. And keeping in mind that divergence is flux per unit volume, so if flux is zero, then divergence is also zero. So what we have here is a physics point of view for computing the divergence. Now, if you want to do that the old-fashioned way, right, if you want to take this formula and start computing partials and deal with, the fact that there is a fractional exponent in the denominator and deal with all the resulting algebra, which, by the way, everyone should do once in their lives, and I think you all have already done yours. I think back in Chapter 3 there was a homework exercise where you had to literally compute the divergence of this vector field, and the answer is zero. And so again, algebra will show it, but I think it's so much easier to think of that divergence as literally flux per unit volume, in which case this result's kind of obvious. Is that cool, everybody? Follow? Yeah.
Yeah, and so where we have the divergence is greater than...
Yeah, I'll get to that. I haven't gotten there yet. Yeah. Okay, so away from the bulb, divergence is zero. Okay, so let's talk about where the bulb is, where the LED is, looking at the actual little LED there. I'm going to put another little sphere, this time around the little LED, and I'm going to make it really, really small, right? I drew it, not extremely small, but I want it to be visible, right? But imagine this blue sphere being like as small as it possibly could be while still containing the entire LED itself. Okay, well, how much flux is going to be measured through this blue sphere? And I claim a lot. Right? And roughly speaking, there's a units for this. With light bulbs, I don't know if y'all bought light bulbs recently, but they have a measuring system for talking about how much light per unit time does this create? And they talk about it in lumens. I don't know if you're aware. But anyway, so a standard 100-watt equivalent bulb, at least the one I bought for my closet a couple weeks ago, if I remember correctly, was 1,600 lumens. And that's a very bright bulb, right? It makes a lot of light. So 1,600 lumens that's a lot of light. Okay, fine. What's the flux then through this little blue sphere? Well, the LED is producing 1,600 lumens, and all of those photons will exit out of this blue sphere. So I can tell you exactly what the flux is through that blue sphere. It's 1,600 lumens. Because every photon created by the LED flies out and therefore contributes to flux through that blue sphere. Okay. Now that's flux. Don't forget, divergence is flux per unit volume. And keep in mind, again, this is supposed to be a really small, itty-bitty little sphere, just barely containing the little LED itself. Teeny, tiny little, very small volume. So what happens when you take a substantial flux and divide by an itty-bitty volume? You get a very large, flux per unit volume, aka divergence. So the divergence is going to be huge on the LED itself, where the photons are being created. Divergence is huge. Does that make sense? Okay. All right. Okay, so there's a couple things I like about this example. One, you may recall, I've pitched the following idea, which I think is really helpful, really important to understanding all this stuff, making it all sort of natural. And it's a weird ask, but even when your accumulating quantity is computed on the boundary, I want you to view it as having actually come from the interior. And here's what I like about this example. This is literally happening here, right? If you measure the flux on this sphere here, if you measure the actual, flux there, and how much flux do you get? Well, 1,600 lumens, right? Where is that coming from? Where are all those photons originating? Are they originating in the glass of the bulb? No, of course not. They're originating at the light source in the interior, right? So this is literally, this is a physical example where what I have kind of pushed this idea that it's coming from the interior. It's literally happening in this case. So when you have a physical model where it's literally happening, I think it makes it a little bit easier. I hope this makes it a little bit easier to digest, that it's a reasonable point of view to take, even in examples where maybe it's not so obvious, right? And I think this one's pretty easy buy, in the sense that, that's the center. Yeah, that's where the light's coming from. It's an LED bulb. All right. The other thing that this is a fantastic little example of is that I've claimed that divergence tells you where that stuff is. We have this accumulating quantity. We view it as a stuff distributed through the interior. And divergence is the density. Divergence tells you where that stuff is. And, this says that at the LED itself, that's where the photons are coming from. And it is. Right? So this is a fantastic example of two of the kind of more abstruse and weird and hard to swallow points of view that I've given you up to now. This is physically manifesting those arguably subtle, difficult ideas quite literally. So, good one to think about, yeah.
Yeah, so can you say that anywhere that's not at the, right at the point where we have the LED, the flux is zero?
I'm going to quibble with your language a little bit. Mm-hmm. At points, we can talk about the divergence, right? If you want to, not the flux, because you can't talk about flux at a point, but you can talk about flux density at a point, and flux density is flux through a surrounding surface per unit volume.
Okay.
So yeah, so the flux on one of these little spheres like this is 0, and the flux density at a point is 0.
Okay.
Yeah, absolutely. Yep. And again, tracks with our point of view of, and to what extent is light coming from there? Well, it's not. This is just empty air. There's no light coming from, there's light passing through there, but it's just passing through. The light source is here where the divergence is, and this is not a light source. And there could be a lot of photons here, but they're just passing through photons. They didn't originate here. Okay. All right. Next example. Just a different kind of a fluid. The important idea that I want to get to with this one is that fluid, not all fluids are the same. Light's arguably kind of a weird fluid. If you think about it, you go back up to here, the light is being generated. We are literally creating photons. That's what light bulbs do. They manufacture, generate photons out of just electricity, energy, right? So, cool trick. Whereas the photon density is not actually changing throughout this process, right? This flow of a fluid is not representing, hey, there were a bunch of photons here, and as they move away, there are less remaining photons. And that's not at all what's happening, right? How many photons there are is pretty constant. And by the way, this is true in this room here. There's various light bulbs. There's light going every which way in all different directions here. But if I were to hold my hands about like this and define kind of a little sphere with my hands and ask how many photons at any given moment are inside of the little sphere I'm making with my hands here, yeah, it's pretty much the same as it is 10 seconds later. There's always just pretty much the same number of photons in there. Right? So density is not changing. We're generating fluid, but that fluid is not collecting or disappearing. So, okay. Now, on the other hand, here's a very different kind of fluid. Let's imagine a gas. Right? And so in my mind, we're out in space somewhere, and there's like a gas cloud or something. And let's imagine that the temperature starts to increase, and if you all remember your high school physics, your gas law stuff, if the temperature increases, that's going to expand, right? And so as the gas expands, it's going to expand kind of outward, you might say, and this vector field, something kind of like this, kind of outward. The farther you go out, the more gas is pushing it along, and so it's moving faster at the edges. And of course, in the middle, if the gas is expanding sort of symmetrically, in the middle, the gas isn't moving at all, right? So something like this would represent this outward expansion of gas. Okay. Now, different kind of a fluid. Is fluid being generated in this scenario? Not at all. We have a finite amount of gas. That's it. There's a finite amount of gas. It's not being created at all. Right? Is the density constant like it is with photons? Not at all. Density here is decreasing. We had a finite amount of gas in a certain amount of volume, and once it expands, that same amount of gas is now in a much larger volume. The density is decreasing, right? So this is a qualitatively different kind of fluid, and so we're going to have to make a totally different interpretation of what divergence, how do you make sense? What does divergence look like in this scenario? Right? And so here's how I'm going to do it. Let's see here. We're going to look at this sphere here. And we're going to think about the flux through this sphere. And I'm going to make a couple observations. Let's see here. The first observation, nice little quickie. Divergence theorem, boom, that's a freebie. Flux is always a triple integral of divergence. That's, write that down. Nice little easy starter example. And by the way, you can compute the divergence here. Let me do this. The divergence ends up being 3K, keeping in mind that this vector field F is what we're taking the divergence of. Now, how did I get 3K there? You need to take this vector form for the vector field and write this out in coordinates. This is kx, ky, kz. And then you take the divergence per the usual formula of that, and you will get 3K. So make sure you can do that. It's a little detail. 10 seconds once you see the right way to do it. Easy calculation, but make sure you can do that. Okay. Now I'm going to make a different argument. And that is, if I'm keeping track, I would like just a little bit more room here. And let me do that also. Ooh, now I can expand. Let's do it like that. So if I'm keeping track of how much gas remains inside of the sphere here, I argue that the flux is telling me the rate that mass of gas inside of the sphere is decreasing. Now, this is a physical appeal, right? But flux represents the act of gas exiting. Whatever M is, whatever the total amount of gas that I have inside the sphere, more flux means this is decreasing at a faster rate. And so I'm ignoring constants here and units, but flux is an indication of a decreasing amount of gas inside of the sphere. Do y'all buy this, that these are the same? Here, let me highlight. So I'm claiming that for this reason, is that. Okay. And then having made that observation, no big deal here, but mass, of course, is an integral of density. That's always, right? That's an old bit of news. And then I'm going to take this negative d by dt and apply it specifically to the density to get that. That's just kind of moving the derivative inside of the integral. Right? Is that cool? All right, and so we end up in this kind of cool situation. I've shown that all of these are equal, and those are equal, and these are all equal. The punchline then being that these two integrals are equal. These are integrals over the same domain. When you have two integrals over the same domain, always equal, no matter what domain you pick, that means that the integrands must be equal. And therefore, we have a nice interpretation of divergence, keeping in mind that integrand is divergence. In this case, with this particular kind of fluid, divergence represents how fast is the density decreasing, right, per this observation here. Oh, I forgot to mention, I'm sorry, I should have mentioned this earlier. It's been a long day. This line of equations down here, I just added to the notes file. I'm sure you noticed. But anyway, brand new. This line down here is the main change that I made. So if you want to get this, the updated file is on the website, the class website, in the folder called Class Materials, right where they always have been. But anyway, that file has been updated. Okay, so we get a different physical interpretation because it's a different kind of a fluid. And just keep in mind that you always have to tailor your interpretation. What does divergence mean? You always got to interpret according to the nature of the kind of the fluid that you're talking about. And think about the setup of the question. Every situation is different. Yeah?
What allows you to bring the d over dt to the integrand?
Yeah. Let's see how to say this. The integral doesn't have anything to do with t, right? So I can think of this integral as representing just a summation of a bunch of terms, right? And I'm applying that derivative to the total. And when you apply a derivative to a sum, you get the sum of the individual terms, or the sum of the individual derivatives. And there are some sticky wickets there, and it's not what Math219 is about. I'm going to just claim that this works fine, and morally because a derivative of a sum is a sum of the derivatives. Yeah. Is that satisfying? Okay. Yeah. Cool. Okay. Different interpretation for different physics reasons. So now just a little bit of a cultural point, and maybe a preview of fluid dynamics courses you might take in your futures. Sometimes you have a fluid that's being generated like a light bulb, right? And also where the density may be changing also, like the gas example. So both of these variables might happen for some kinds of fluids. And if you want to discuss examples, come discuss with me in office hours. I'll tell you a couple of examples I'm aware of. But in other situations, you're more likely to see them. It turns out that flux relates to how fast you're generating fluid and how fast the density is changing by way of this equation right here. And my picture for how to think about this is if you have some region, maybe I'll add this at some point. If you are generating fluid, and I'm going to represent the generation of fluid by, fluid being inserted into the region, I'm going to point out there's really only two things that can happen. Once fluid has been generated, it either stays in the region, in which case it contributes to how fast the quantity of fluid is accumulating, is collecting in the region, or it doesn't stay in the region, which means it would have to leave the region, which means it's going to contribute to the flux. So generated fluid either stays in and contributes to the blue term, or it doesn't stay in and it contributes to the purple term. And so we get this nice little easy relationship between these variables. And so this is a kind of a foot in the door for understanding flux, and then likewise for understanding divergence if you have one of these kinds of situations. So, and again, I don't want to go down this particular bunny hole. Is not what this course is about, but I just wanted you to be aware that in some sense the two examples on the previous page are the extremes in a sort of a continuum in between that fluids could be. Okay. All right. So let's talk about gravity a little bit. Y'all probably remember the formula for a gravitational field. This is from chapter 3. It's inverse square radial. Way back, chapter 3. Inverse square radial. Wait a second here. Inverse square radial. Yeah, our light bulb example is inverse square radial. Now, this is what I like to call an eyebrow raiser. Right? Wait a minute. Structurally, the flow of light out of a bulb is mathematically indistinguishable from gravitational fields? That's weird, right? Coincidences happen. But very often when you see what looks like it might be a coincidence, very often it's not a coincidence. Very often you've stumbled onto a little reality. Right? And so there is a theory out there, and this is a theory, and I'm not an expert in this area, and so as to whether what I'm about to say is actually true or not, I don't know. But a plausible theory is that, in the same sense that light is communicated by little particles that shoot outward from bulbs, that likewise gravity might be communicated by little particles that shoot outwards from mass. And if you think about it, if that were the case, your point mass, if you have a single point mass like this, just like if we have a single point, light source, little particles shooting out of a little piece of mass, little particles shooting out of a light source, yeah, of course they would be the same field. They're really fundamentally the same idea. Right? So there is this theory out there that that's what gravity is. That gravity is communicated by mass creating and emitting particles. And these particles have been named gravitons. Now, this is just a theory, right? This doesn't prove anything, but man, it acts like this is true, right? Look at the formulas. It's again, this doesn't prove anything, but it's very suspicious that it could be like this. Now, I've made some observations in the past. I like the little phrase, if it looks like a duck, quacks like a duck. Might be a duck, right? It's not necessarily a duck, but it behaves like a duck, so you can treat it like a duck, and it'll always lead you in the right direction, right? And I think this is a pretty good idea. All exceptions granted. So what we're going to do with gravitons in this class is pretend that they're real, and whether they are or not doesn't matter. Gravitational fields behave as if gravitons are real, so we're going to pretend gravitons are real, and that will allow us to treat gravity with a nice little point of view, and we will get all right answers. Everybody buy it? Okay. All right, so whether they're real or not, I don't care. And by the way, I've had conversations with physicists about this, and long, laborious answers, but the most persuasive argument that I've heard fairly recently, if I were a gambler sort, I think I bet that they aren't real. But again, not my area of expertise, and it doesn't matter. Okay, so what we can do with this really powerful idea, deceptively powerful, in fact. It doesn't seem like this is a deep point, but we're going to be able to draw some really amazing conclusions. I'm going to start with this equation right here. This is nowhere near as hard as it looks. We have this negative 4 pi g on both sides. That's just a shared constant on either side of the equation. We can just ignore that. Notice that what remains is the very familiar statement that mass is a triple integral of density, which is old news. All right, so that top line, I think, is no big deal observation. Let's see here. This is where we're going to use the graviton point of view. I claim mass is proportional to flux. More mass gives more gravitational flux. Really not obvious if you think about this from a gravitational fields point of view. But if you take a graviton point of view, this becomes really clear because mass produces gravitons. More mass, more gravitons. What do gravitons do? Gravitons flow away. In particular, they flow through our surface, our closed boundary surface. So more mass produces more gravitons, which is going to therefore create more flux. And so from that point of view, again, thinking about mass as creating gravitons, and gravitons create flux, mass should be proportional to flux. What do you think? Takes a little bit of digesting. Again, it's kind of a weird point of view on gravity, but let's say it this way: if I had a light bulb in there instead of mass, if I had a light bulb creates flux. If I had two light bulbs, I would be creating twice as many photons, and that would go through the bulb and make twice as much flux. Right? So same idea, just replace bulbs with mass and photons with gravitons. Point of view. And then lastly, we write down Gauss's divergence theorem. And altogether then, we have the same scenario we had on the previous page. This is equal to this, which is equal to this, which is equal to this, which means that these are equal. And again, this is for any region. And so if we're looking at integrals on any region, this integral is always equal to this integral, no matter what region R we're talking about, then I claim that means that the integrands have to equal. And that is a really powerful statement about the gravitational field. No matter how your mass is arranged, your mass could be anywhere, any which way, that mass will create a horrendously complicated gravitational field, which I don't want to write down. I could write it down, but it'd be a real monster to write it down. But the divergence, proportional to density. Simple as that. That's a really natural, powerful conclusion. And it all comes out of two big points, right? The graviton point of view gives us this connection, and the divergence theorem gives us that connection. So, divergence theorem, again, a big deal in being able to make these conclusions. Okay, why do you need to understand gravitational fields? If you're not planning to be a cosmologist or an astronaut, who cares? Right? Well, here's a case for why I think, aside from, again, just general science and engineering cultural awareness of cool facts, let's look at electric fields. And electric fields, inverse square radial, just like gravitational fields. They're mathematically identical to gravitational fields. And this was a massive realization for me when I was studying physics, again, decades ago, that electric fields are, physically very different, but mathematically it's just like gravitational fields. I didn't have to, come to understand a completely new kind of mathematical construction to be able to make sense out of electric fields. Just pretend like charges are mass. And the electric field is the gravitational field. It's pretty much the same. The only difference is constants and units. And physics interpretations, of course, can be different. So this is the same argument that you get if you go through the same, we have a shared constant that we can ignore. Charge is an integral of charge density. And you make some argument about how, flowing particles, and it's kind of like light, etc. And then you write down the Gauss's divergence theorem, and then you conclude a nice result right here. And this is called Maxwell's first equation. So those of you who've taken E&M classes probably recall Maxwell's equations. And this is one of them. This is the differential form of one of them. And by the way, this right here in the first place is the other form of the same equation. So this is also called Maxwell's first equation. And here's another thing that seems super weird when you first see this stuff. Certainly when I first saw these equations in a high school physics class, and I was like, how are these the same equation? They seem really different. This one's about flux. This one's about divergence. Right? And I didn't know anything about the divergence theorem at the time. And so they just seem completely different, completely unrelated. The divergence theorem, though, of course, is the thing that makes these relatable. The fact that you can write down the divergence theorem allows you to see that the equations on the left, this equation on the left is just kind of an integral on both sides of the equation on the right. And the divergence theorem is what allows you to make that connection again. So really, really important to understand the divergence theorem if you want to understand different points of view on electric fields and charges and flux and related ideas. Important player. Okay. All right, how we doing? Is everybody okay? So all of these examples together, let me sort of bring it all together. Electric fields, all the engineers in the room definitely need to understand electric fields. Okay, what's my offering for how you should think about electric fields? Think about it in terms of gravitational fields. Gravitational fields are relatable. Mass, I've been pretty comfortable with the idea of mass since I was old enough to understand words, right? Not a hard concept. Gravitational field, yeah, you drop stuff, it falls down, right? Really easily relatable idea, right? Nothing deep or weird. Much easier ideas to understand than electric fields and electric charges, which are so non-relatable, humans didn't even notice them until pretty recently. I mean, like a couple hundred years ago. That's not that long. They're really subtle and unrelatable, and certainly not in an everyday sense, right? So I find all of this to be much less relatable. I find all of this to be much more relatable. So use gravitational fields as a model, as an intuitively satisfying model for understanding electric fields. And then next question, how do you understand gravitational fields? Light bulbs. I think it's a really, really nice, simple, natural, again, very relatable way of thinking, and just a much more convenient metaphor, I think, than otherwise. So, okay, so there's a bunch of physics. Okay, real quick, we're going to do a little bit of Stokes' theorem here. We're not going to be able to get to the big theorem, but let me hit the broad strokes. We're going to define a convention about boundaries. I'm going to observe an accumulating quantity, and theorem falls into our laps. Let me just remind you, as soon as you have an accumulating quantity, you can treat it like stuff. It might actually be stuff, and you just didn't notice yet that it was stuff, right? But you can certainly treat it like stuff. Stuff is distributed over the interior, has a resulting density, and you can compute stuff as an integral of that density. We've done this in a lot of different contexts. We did this with mass. We did it with circulation to get Green's theorem. We did it with flux through a curve to get the two-dimensional divergence theorem. We did it with change to get the fundamental theorem of calculus and the fundamental theorem of line integrals. That's like 5 different examples, right, of where we've made this argument before, that accumulating quantities behave like stuff and are integrals of densities. Right? So that's all we're going to be doing. Now, I do have to establish what the rules are about the word boundary. Remember, the word boundary is a loaded word. It means oriented according to certain convention. The convention is that whatever your surface normal is, if you're thinking about the orientation on the boundary curve, whatever your surface normal is, put your thumb of your right hand in the direction of that surface normal. Look at your fingers and see how your fingers point kind of around that normal vector. That will create what I like to call a swirl. And now just ask yourself, okay, that swirl, right? Again, thumb in the direction of the surface normal, fingers defining a swirl. As that swirl kind of side swipes against the boundary, which way does it go? And you'll notice that in this case, it goes that way. All right, so that's the convention. I know it's a weird one, right? It's an oddball little convention, but given an oriented surface, this then is what we call the induced orientation on the boundary. Given a surface, there's the orientation on the boundary. Weird little rule. And with that rule established, boundary circulation accumulates. This little piece of surface, the boundary circulation goes like that. That follows our rule. This little piece of surface over here, boundary circulation goes like this, again following the same rule. Do these add up as they're supposed to? Well, I'm a little concerned about this stuff in the middle, but that stuff in the middle, just like every other example that we've seen, we drew a picture morally identical to this when we wrote down Green's theorem. And the whole point is that on this shared little edge here, on that shared purple edge, we're going that way as part of the green boundary, we're going the other way as part of the blue boundary, and they cancel. Whoops. All that cancels, and notice, as required, we get the boundary circulation of the whole. So boundary circulation accumulates. And we're out of time, but because it's an accumulating quantity, it behaves like stuff, it has a density, and you can write down a theorem. So we're going to pretty much pick up with this on Monday a week from today. I'll review, to remind you what's going on, but pretty much we have this theorem. Okay, see y'all later. Have a good weekend. Have a good break. No, it's not a weekend. Have a good Thanksgiving break. See y'all in a week. Don't forget about attendance if I didn't already get you.